In this video, we'll discuss problems based on Roth-Harvest criteria. Refer the characteristic equation given by h to the power 4 plus 25s cube plus 15s square plus 20s plus k is equal to 0. Determine the range of value of k so that the system is asymptotically stable, and b the value of k so that the system is marginally stable, and the frequencies of sustained oscillations if applicable. So we have to find out the value of k here, and we have to find out for that value of k system will be marginally stable, and we have to find out the frequency of sustained oscillation omega value we have to find out. So now by using characteristic equation we can write Roth array. So it is h to the power 4, rho is 1, coefficient of square is h square is 15, coefficient of h to the power 0 is k. Then s cube rho, so the coefficient of s cube is 25, coefficient of h to the power 1 is 20, and we can write. So now we go to two rows, and for the next row, that is a square row, we have to simplify. We have to take previous two rows. It is matrix we have to write 1 25 15 20 divided by 25, and we have to multiply. We will get 14.2, and a square rows second column is 15 20. Second row we have second column we have to leave. It is 125 k and 0 divided by 25. We will get k. And in the same way, if we find out the same concept, if we apply, we can find out other row values also. It's for one is we'll get row first column is 20 minus 1.76 k. As for 0 we'll get k. And for stability now, see from in the first column we can see that all positive values, but there is a value with the k. Okay, that is h for 1 row is 20 minus 1.76 k. So for stability, we should get some value with a positive constant, right? There should not be any sign change. So we can write whole value 20 minus 1.76 k should be greater than 0. That is our assumption. If it is greater than 0, positive value, any of the value, then it will be stable, right? Positive value. And we can write 20 minus 1.76 is greater than 0, or if we find out, if we simplify and if we find out k is less than 11.36, we will get. So k, if we want to substitute proper value of k, then it should be 11.36, or it should be less than 11.36. If it is less than 11.36, then we will get a positive value here. If we substitute for this 20 minus 1.76 into k, in the value in the place of k, if we substitute value it is less than 11.36, then we'll get this value as a 0. It will be greater than 0, some positive value will get. If it is 11.36, then it may be 0. If it is greater than 11.36, then we'll get a negative value. For h to the power 1 row, we'll get first column value as negative value, so then it is unstable, there is a sign change. So to get positive value, the value of k should be less than 11.36, and the last row assumption is k should be greater than 0. Thus the system is stable for k is greater than 0 and less than 11.36. Understood? It should be less than 11.36, then the system is stable. When k is 11.36, the system is marginally stable. If you substitute k as 11.36, we will get 0, it is marginally stable. The auxiliary equation we can write, if it is 0, for margin stability, if it will be 0, as for one row will be 0. Then we can write auxiliary equation by using previous row, that is s square row. It is a of s is equal to 11.2 s square plus k is equal to 0. So here k is 11.36. So I can write a of s is equal to 14.2 s square plus 11.36 is equal to 0. See now if we simplify this one, if you simplify this equation 11.14.2 s square is equal, I can write minus 11.36. or s square is equal to 11 minus 11.36 divided by 14.2. If we simplify this one, we will get s is equal to plus or minus j into 0.894. So now if we compare this one with s is equal to plus or minus j into omega, then omega is equal to 0.894. So the frequency of sustained oscillation, that omega is equal to 0.894 radians per second. So in this way you can simplify this type of problems. So we'll see one more problem. Refer the characteristic equation given by h to the power 4 plus k s cube plus 2s square plus k plus 1 into s plus 10 is equal to 0. Determine the range of k so that the system is stable, and the value of k so that the system is marginally stable, and frequency of sustained oscillations. It's like a previous problem. So first, by using characteristic equation, we can write root array. So we'll get this type of root array. In the first column, we'll get 1 k, k minus 1 divided by k. Next value is minus 9 k square minus 1 divided by k minus 1, and last value is 10. So the first column, some we have not received all the numerical values. So the values are with k. So now we have to find out the value of k, or range of value of k for the stability. So for stability, from equation or from row 2 or s cube row, we can write k, it should be greater than 0 for stability, right? Positive value will get one assumption. And from the next row, it is k minus 1 divided by k should be greater than 0, or else if we cross multiply, then k minus 1 should be greater than 0, or else k should be greater than 1. See, k minus 1 greater than 0, or else if you simplify, k should be greater than 1 we will get. Or from the next row, h to the power 1 row, it is minus 9 k square minus 1 divided by k minus 1 greater than 0, or else minus 9 k square minus 1 should be greater than 0 if we cross multiply, or else minus 9 k square minus 1 greater than 0, or else if we simplify this one, we will get k should be greater than or equal to plus or minus j into square root of 1 by 9. So for a linear system, k is always real. Hence, the last condition cannot be met by any real value of k. Thus, the system is always unstable. So then we'll see limitations and advantages in the next video. Thank you.